Hello everyone, welcome to Gate Pass. In this video I am going to take the remaining problems related to thermodynamics that appeared in year 2007 Gate paper. Okay, so the first problem, it asks you to tell which one of these plots it represents the Carnot cycle. So before going through these plots, we will first briefly see what is a Carnot cycle. So you all know that a Carnot engine, it operates between two thermal reservoirs. The high temperature thermal reservoir is known as source and the low temperature thermal reservoir is known as sink. Okay. So on PV plot, your Carnot cycle looks something like this. It is made up of four reversible processes. Okay. So there are four reversible processes. The first one, A to B, it is a adiabatic compression. So it's a reversible adiabatic compression. You all know that if a process is reversible adiabatic, then it is isentropic. That means the entropy remains constant. Okay. So the temperature rises from that of the sink to that of the source. Okay. So during this adiabatic compression, your temperature rises from Tc to Th. After that, there is a isothermal expansion when the working fluid is in contact with your high temperature reservoir and it absorbs in QH amount of heat and it expands isothermally. Okay. In this case, the work is now done by the system. Okay. After this, it is followed by a CD process, which is once again a adiabatic expansion. Okay. So in this process also you obtain certain amount of work, and when it expands adiabatically, the temperature drops from TH to TC, that is from the source to the sink temperature. After that, again you have an isothermal DA, okay, where the working fluid, it rejects QC amount of heat to the low temperature reservoir and the system is brought back to its initial state. Okay, so you have, this is one isothermal which is at temperature TH, this is one isothermal which is at temperature TC, and you have two adiabatic expansion and compression. So you have two reversible adiabatics. Okay. So we will be looking for a graph which says that you have two processes with constant temperature and two processes with constant entropy. So let's see the first option. We have already seen that on PV plot your Carnot cycle looks something like this. There are no straight lines, so straight away your option A is wrong. Since you do not have any constant volume process in a Carnot cycle, so your option B is also wrong. Let's see over here. You do not have any constant pressure process. Once again, then this option is also wrong. Let's see option C. You have two constant temperature process and you have two constant entropy process. That's what we see over here. Okay. So your option C is correct. You have two isothermals and you have two isentropics. So this option C, it represents the Carnot cycle. Okay. So the next problem which I am going to take is question number 34. It talks about the vapor phase hydration of ethylene. The reaction is in the gas phase and it is given over here. Okay. So to start with, you have 2 moles of equimolar feed. That means you have 1 mole of C2H4 and 1 mole of water to start with, and you do not have any product. Okay. Now they say that the chemical equilibrium is achieved at temperature of 400 Kelvin and a pressure of 3 bar, and the delta G0 for this reaction is given as 4000 joules per mole. Now they have asked you to give the equation, equilibrium equation, in terms of epsilon. Okay, so 4 options have been given and you have to choose the correct one. Fine. So we have seen such type of problems before as well. So what I have told you, first of all, write down the equation which you have to use. So the equation was product over all I, okay, phi I cap yi p upon p naught raised to nu I, that is equal to k. Okay, so this was the equation. So you have to write down this equation first. Now simplify this equation. So since no information is given about the fugacity, so assume that this reaction mixture it behaves ideally. So this goes to 1. Okay, now you have been given that the pressure is 3 bar, and you all know that this pressure is taken as 1. So your P naught is 1. Now what I will do is, I will separate the two terms. So product over all I, yi raised to nu I, I am going to keep like this, and P upon P naught if I take out. Okay, then since the bases are same and you will have all nu I, the power, it will get summated. Okay, so bases are same, in multiplication then powers are added, so you have summation over all nu I, and you know that summation over all nu I is your stoichiometric coefficient, that is denoted by nu. Okay, so it will be raised to nu, that is equal to k. Now let's find out what is nu first. So nu I for C2H4 it is -1 for H2O, and for ethanol it is +1. So -1, -1, -2, +1, -1. So your nu is equal to -1. Fine. So that means now I will further simplify the equation. So product over all I, yi raised to nu I, that is equal to k times, now I will take it on the other side. So it will be P naught upon P raised to nu, and that will become k times, what is P naught? 1, and what is P? That is 3. 1 by 3 raised to -1, so I can write it as 3k. Okay. Now next step will be to calculate what is k. Okay. So k, we all know that it is given by exponent of minus delta G0 by RT. So it will be exponent of what is delta G0. So you have minus 4000 divided by R, that is 8.314 times T, and that is given as 400. Okay, do the calculation and you will get the value of K as 0.3. Okay, so your K value is 0.3. That means now your equation is reduced to, so I will erase everything from the board and just write the simplified form of this equation. Okay, so I have, let's see, product over all I, yi raised to nu I, that is equal to 3 times k, k is 0.3, so 3 times 0.3, so it is 0.9. Okay, now we have to write down the mole fractions in terms of your extent of reaction, and we know that yi, that is given as Ni0 plus nu I epsilon divided by that is divided by N0 plus nu epsilon. Okay, where Ni0 is the initial number of moles of any species I, nu I is the stoichiometric coefficient of species I, N0 is the total number, total number of moles, and nu is summation over all nu I. Okay, so this is the formula which we are going to use. Now for simplicity, I am going to say that this is my component A, this is my component B, and this is my component C. Okay, so I can write Ya, that is equal to, now they have given that there is 1 mole of C2H4, write it down. So you have 1 mole of C2H4, 1 mole of H2O initially, and you have 0 mole of C2H5OH. Okay, so Ni0 is 1 for component A, so 1 minus epsilon upon 2, nu is summation over nu I, and that is -1. Okay, so this is your mole fraction for component A, that is ethylene. Similarly, I can write my Yb, that is again equal to 1 minus epsilon upon 2 minus epsilon. Okay, now let's write Yc, that will be equal to, initially you have 0 number of moles, so it will be epsilon upon 2 minus epsilon. Okay, so now I am going to plug these values over here. Fine. So for product, Yc, that will be raised to 1, and Ya and Yb will be raised to -1. So they will appear in the denominator. So I can write straight away epsilon upon 2 minus epsilon, that is divided by 1 minus epsilon upon 2 minus epsilon multiplied with 1 minus epsilon upon 2 minus epsilon, and that is equal to 0.9. Okay, simplify this equation. One of this will cancel, and what you are left with is epsilon multiplied with 2 minus epsilon upon 1 minus epsilon square minus 0.9, that is equal to 0. Okay, so this is your equation at equilibrium. Okay, now see which one of the options it matches with our answer. That is, I think, option D. Okay, so your option D is the correct one. So it's a very simple problem. I have told you how to attack these problems. First of all, write down the general equation, then simplify it according to your question. Then go ahead and find the value of K, which was 0.3 in this case, and then write down all the mole fractions in terms of your extent of reaction. Plug everything back in your original equation and then solve it. Okay, so very simple question. So next two questions which I am going to take, they were common data questions. Okay, and this question, it talks about a perfectly insulated cylinder. The total volume of the cylinder, that is the entire volume, that is equal to 0.6 meter cube. Okay, now it is divided into two parts by a frictionless piston, which I have drawn over here, and it is held in place by a stopper. Okay, now in the smaller compartment of volume 0.2 meter cube, you have an ideal gas. So in this compartment you have an ideal gas which is at 6 bar and 100 degrees centigrade. Okay, now the first question, it asks you that if at any instant of time this stopper is removed so that your piston can move freely to the other end, then what will be the final temperature? Okay, now they have given you 4 options. Let's see what is the answer. So first of all, you will see that this is a perfectly insulated cylinder, so there is no heat exchange. Okay, so your Q is equal to 0. Now your piston is moving against vacuum, so there is no work which is being done by the piston. Okay, so again your work done, that is also equal to 0. Okay, so if I write down my first law for a closed system, that is delta U is equal to Q plus W, where my sign convention is that the heat supplied to the system is positive and work done on the system is positive. Okay, since Q and W both are 0, that means that my delta U, that is equal to 0, or I can say that my U initial, that is equal to U final. Okay, for an ideal gas, you know that your internal energy, it is a function of temperature only. Okay, so if my initial and final internal energies are same, that means my temperature also remains the same. So that means my Ti, that should also be equal to Tf. So my final temperature should remain the same, that is at 100 degrees centigrade. So out of these 4, option D is correct. Okay, so this was the first part of the problem. Now let's go to the second part. So the next part of the problem, that is question number 83. It says that now you have removed the insulation. Okay, and now the piston is moved back so as to restore the original state of the system. Okay, so what you are doing, you are moving back the piston so that it comes back again to the same point, and such that the gas inside is again at the same temperature, pressure, and with the same volume. Okay, so this is what we are doing, and this is achieved only by doing work on the piston. Okay, there is no heat which is supplied to the system, only it can now reject heat. Okay, so let's assume that we are doing this compression through a reversible isothermal process. Okay, because initially you have 100 degree of temperature and final temperature also you want to maintain at 100. So we will assume that let's do it through a reversible isothermal compression. Okay, now since this is a closed system, I can write down my first law, that is delta U is equal to Q plus W, where my sign convention is that heat supplied to the system is positive and work done on the system is positive. Okay, since the initial and final temperature both are 100 degree, so your delta U is equal to 0 because temperature is not changing. That means that your W will be equal to minus Q. Okay, so whatever work which we are doing in order to compress this gas, okay, this is all lost to the surrounding as heat. Okay, this is what it means. Now you have to find out what will be the work which is required, the minimum work which is required. Minimum work will be for the reversible process. Okay, and how it is given for any mechanically reversible process, you have the work done that is given by minus integral PdV. Okay, since this is an ideal gas, I can write down now P in terms of V. Okay, so I have this equation PV is equal to nRT. I cannot take N equal to 1 because in this case the total number of initial number of moles are already given. Why? Because you have volume which is fixed, pressure and temperature are fixed, so you can use this equation to calculate your number of moles N. Okay, but we will not find that, we can bypass it. Okay, so let's write down now your P, that is equal to nRT upon V. So I am going to plug this over here and find out what will be work. So that will be equal to nRT dV by V. Okay, now nRT, because this is an ideal gas, what it says, your temperature is constant. Okay, so you have your Pi Vi, that is equal to Pf Vf. Fine, that remains constant now, and that is equal to your nRT. Okay, so instead of nRT, I can write down what my Pf Vf. What is the final pressure and final volume? In this case, final pressure is 6 bar and final volume is 0.2 meter cube. So instead of nRT, I can write down Pf Vf. Okay, so what is now your Pf? That is 6 bar. So 6 into 10 raised to 5 Pascal. Vf is 0.2 meter cube. dV by V, if I integrate it and put the limits from Vi to Vf, I have ln of V. When I apply the limits, it will be ln of Vf by Vi. Vf is 0.2 and Vi is 0.6. Okay, I have to just solve this and find out the answer. If I solve it, what answer I get is 1.318 into 10 raised to 5 joules. Okay, or since the answer is given in terms of kilojoules, so I will change it. So kilojoules will be 10 raised to 3 joules. So 2 I will assimilate over here. So it will be 131.8 kilojoules. Okay, round it off. It will be 132 kilojoules. Let's see, option C is correct. Okay, so very simple problem. You have to just know how to calculate the work done. The next problem is very interesting. It says that your ideal gas, it goes from temperature T1 and pressure P1 to final temperature T2 and pressure P2 in a constant volume process. Okay. Now, in order to calculate the change in enthalpy, what variables do you require? Okay. So, we know that irrespective of the process which is an ideal gas is going through, you can always calculate your change in enthalpy dH. Okay. That is equal to Cp times dt, or I can integrate it and say that the change in the enthalpy, that is equal to Cp T2 minus T1. Okay, so in order to calculate the change in enthalpy, you require only Cp, T2 and T1. So your option B is correct. I will elaborate a little more on this because you might say that okay, this equation it should be applicable only for a constant pressure process, because how do you define your Cp? You say that dH upon dt at constant pressure, that is defined as Cp. Okay, so you may argue that your for only a constant pressure process you can write this. Okay, but let's see what is happening over here and why I am saying that this equation will be valid irrespective of the process which is taking place on an ideal gas. Okay, so you all know that for an ideal gas your U is a function of temperature only. Fine. Now how do you write H? H is written as U plus PV. For an ideal gas, I can, instead of PV, I can write RT. Okay. U is a function of T. RT again a function of T. So I can also say that H is a function of T only. Okay. So for an ideal gas, your H is a function of temperature only. Okay. To understand this, I will plot a graph. Let's say that I am plotting H over here and P over here. Okay. Now since H is a function of temperature only, so I will have one value for T1 and one value for T2. Okay. Now, irrespective of what type of process is taking place, if I am taking the system from temperature T1 to T2, whether through a constant volume process or a constant pressure process or a polytropic process, whatever. Okay. If I am going over here or like this or this, okay, always the enthalpy value will be determined by the final temperature T2, because for an ideal gas it's a function of temperature only. Okay, so irrespective of the process by which we reach this temperature T2, once the temperature T2 is reached, your delta H is fixed. Okay, so you can use that equation that your dH, that is equal to Cp dt. Okay, for an ideal gas you can use it for any process. Fine. So that's why you require only Cp, T1 and T2. So I hope it's clear to you. Now let's move to the next problem, that is question number 7. It says that the change in entropy of the system, delta S system, it is denoted by delta S system, okay, undergoing a cyclic irreversible process is greater than 0, equal to 0, less than 0 or equal to delta S surrounding. Okay, so read carefully this problem. Okay, let me draw a hypothetical irreversible process on a PV diagram. Okay, so let's say this is my cyclic process. So I'm going in this direction and coming back to the same point. Since your entropy is a state function, so whether this is a reversible cycle or an irreversible cycle, if you come back to the same point, okay, then your entropy at this point will remain fixed. Okay, so that means your change in the entropy of the system, that will be equal to 0 if you are returning back to the same point. Fine. So that's why you have the answer, which is that your delta S system, that is equal to 0. Okay, don't get confused. If they ask you that the total change in the entropy, whether that will be equal to what, then you can say that the total change in the entropy, it will be greater than 0. Okay, or if they talk about what will be the change in the delta S surrounding, okay, that will also be a positive quantity. But here they are asking you only about the change in the entropy of the system. So be careful if you return back to the same point. Since entropy is a state function, then the change in entropy of the system will be equal to 0. Okay. So the next problem is, it says that the parameters A and B in van der Waals equation or any cubic equation of state, it represents which one of these. Okay. For your reference, I have given the van der Waals equation of state, but before going through these, let's say how your ideal gas is defined. So ideal gas is defined by saying that the intermolecular interactions are negligible and the volume occupied by the gas molecule is also negligible. Okay, so when you are writing an equation of state for a real gas, then you have to introduce parameters which takes care of both of them. Okay, so there in a real gas there are intermolecular interactions and parameter A takes care of it. Further, in order to take care of the molecular size, then you introduce your parameter B. Okay, so out of these options, your option D is the correct one. Let's move on to the next question. If Mi is the molar property of pure species I, Mi bar is the partial molar property, MIR is the residual property and MIE is the excess property for any species I, then the mixture property M of a binary non-ideal mixture is given by which one of them? By now you know that a mixture property, it is calculated from the partial molar properties and the relation which gives it is known as summability relation. So your option A, that correctly states your summability relation x1 m1 bar plus x2 m2 bar. So this is the correct option. So thanks for watching this video, and if you like this video, please don't forget to subscribe to my channel and hit the like button. Thank you very much.